we have here is the first half of Unit 4, a study guide answer key. Unit 4, we actually split into the end of first semester and beginning of second semester because it's a pretty big one. And the first half, what we saw in the first semester was basic probability rules and making tree diagrams, whereas the second part, which was chapters 15 and 16, involved geometric and binomial distributions. Not sure if you remember that entirely. Bernoulli trials were part of that as well. And we'll save that for a separate study guide and video. So this one's going to be about the first part of Unit 4, Basics of Probability, and what you can do here and what you see. This is an answer key. I've already written it all out, the examples as well as the definitions. You can pause this at any time to write down what you need. And here we go. So to start with, probability in general is just the number of times an event can occur divided by the total number of possible outcomes. And it always will have an answer between 0 and 1. 0 meaning something's impossible and will never occur. 1 meaning it will always occur. Now, things that you may hear, and I want to make sure you know what they're asking. So if you're asked to find the probability of an event not occurring, that's known as its complement. We sometimes called it the leftovers because an example would be if I told you there's a 20% chance of rain, there's an 80% chance it doesn't rain. And you find that number by simply subtracting the one probability from 1. So again, if I said what's the probability of it not raining, it's 1 minus the probability it's raining. And sometimes you kind of just do that mentally in your head. You don't have to write 1 minus it, but that is where it comes from. Now, kind of an extension of that would be if you're asked about the probability of an event occurring at least once. Now, I will say anything with at least once, these have to be independent events occurring with replacement is another way of thinking about it. So if I said to you, we're playing cards and I'm dealing you cards, and I say, what's the probability, and if I deal you 4 cards, that you get at least 1 ace, you couldn't do that. Because once I've given you an ace, there are no longer 52 cards in the deck and there's no longer 4 aces. You're changing the probability each time. But if it's a problem, and where we've seen this in the past, let's say a traffic light is green 20% of the time, and I ask you what's the probability it's green at least once in the 5 days you drive to work. Well, each day is independent, and each time you approach the light is an independent event with that 20% likelihood. So that's a situation where you might see at least once. How you'd actually answer that, the formula for that, the probability of something happening at least once is 1 minus the probability something never occurs raised to the n power, where n is the number of trials. So again, if we think of that traffic light example, what I kind of just said out loud was if a light is green 20% of the time, and I say, what's the probability it's green at least once? You'd write 1 minus the probability it's never green, which is 0.8, raised to the 5th. So it's sort of like a complement, but with a little bit of a twist regarding what you put in the parentheses here, as well as having an exponent. All right, so if we move on from there, another word you've probably heard many times would be mutually exclusive. Sometimes calling them disjoint makes more sense because disjoint implies that there is no joining of them, and that's exactly what mutually exclusive means. There's no intersection. So mutually exclusive or disjoint events are events that do not intersect. There's no common or overlapping situation. All right, another vocab term we've heard a lot is or. You may be asked to find the probability of one thing or another occurring. Now, you'll see that there's 2 formulas here. One says when events are disjoint, and then there's the general rule. I wouldn't even worry about this one because honestly, the one here that I have circled in red, that always is true. So the word or means the same as the word union in set notation, and it means you're adding. Or means add. So if I say what's the probability of this or that occurring, you add the 2 probabilities. Now you'll notice if there is overlap or intersection, then you would subtract that off. So a formula above doesn't have that subtraction part, but frankly, you can't go wrong using this one. Because if there's no intersection, okay, then you write -0 at the end. But at least you know that you have to remember that and account for that. And we'll see examples with that momentarily. Now, just like the word or gets used in probability, so does the word and. The word and can often imply multiplying, as you can see right here. Sometimes it implies that it is consecutive events, and that usually, again, indicates you're multiplying. Where you may see something like this would be, if I said, what's the probability of you on a rolling a pair of dice? What's the probability you roll a 3 with your first die and a 3 with your second die? So there's that word and the probability of A, well, that's if it's rolling a 3, that's 1 out of 6. And the next time you roll something, it's still 1 out of 6, and you would multiply it. And that's why rolling a pair of dice has a sample space of 36, because there are 6 times 6 or 36 possible outcomes. Now, sometimes one event is not independent of the other. So the dice example, each time you roll, it's independent. But if it was like dealing cards, well, once I've given you an ace, let's say, the probability of getting an ace the next time is different. So that can lead to some confusion. And that's what we see with these coming examples. Now, if you're looking at this and you're like, why do you have this general rule formula again? There's a reason this is here. These formulas are nearly identical, except for that. And basically what this means right here, this is proving that these are independent. And we're going to see that in just a second. But by definition, two events are independent if the probability of B occurring, let's say, is the same as the probability of B occurring given that A has already happened. So we'll look at that in just a second. But again, technically, just like we saw with the OR formula, this guy is technically the correct formula. So if you want to just know that one or just remember that one, you can. And we'll talk a little bit more about the idea of independence in just a second. So first, let's talk about consecutive non-independent events. So I keep referencing cards. Let's talk about it. So if you're not familiar, and I doubt there will be anything like this on the AP test, they're not assuming you understand cards. They would have to tell you. They would have to say something in the problem like, in a deck of cards, there are 52 total cards, 13 of which are spades. Like they would tell you that. And then if that's the case, they're asking what's the probability you are dealt 3 consecutive spades. Okay, well that's where again, consecutive events means you're multiplying, but as you can see here, the denominator keeps decreasing by 1 because I keep dealing you 1 card. Therefore, there is 1 less card in the deck each time. Similarly, I keep dealing you the same card. I'm dealing you spades. So what you're writing in these parentheses are the probabilities. There is a 13 out of 52 chance you get a spade with your first card. But if you did, then there is a 12 out of 51 chance you get one on your second turn, because there's 1 less spade and there's 1 less card. And then the same with the third one here. So these are not independent because what you were dealt first impacted the probability of the likelihood of getting a spade with your second card and so on. If they were independent, you would just keep writing the same probability and raise it to the nth power, where n's the number of trials you're conducting. So let's talk about something I referenced over here, this line right here. I didn't really tell you what that meant, and we're going to talk about that here. That's the conditional probability terminology, and a lot of times we say that is given that. So technically, if the way you'd interpret this or read this right here, you would say the probability of B given that A has occurred. What does that look like as a formula? It's this, where this is like saying A and B, and this is like saying A has occurred. So something you may remember if you see the words given that is always indicating to you whatever you hear after given that is the denominator. So once you read the phrase given that, the denominator is whatever comes after it. Now, what this is basically saying here is two things are independent if the probability of it and the probability of it in a conditional sense are the same. We'll see that in an example in just a second. All right, another thing that we talked about was relative frequency. This is like if you were conducting an actual experiment or study, it's your observed frequency. So, you know, in a perfect world, if I flipped a coin 10 times, I would get 5 heads and 5 tails. However, maybe you flip a coin 10 times and you get heads 8 times. That's the relative frequency, 8 out of 10, let's say. Now, technically, theoretical probability or expected, you're expecting 5. And there's a rule, and there's no such thing as the law of averages. If you've ever heard that, that person is misspeaking, but there is a law of large numbers, which says if you do something more and more and more and more and more, as the number of trials increases, your answer for what you're observing will approach what you're expecting. So in this case, don't worry of it so much as out of 10. If you know 50% is the there's the probability of tossing heads on any given situation, maybe after 10 tosses it was 80%. But maybe after you toss a coin 100 times, you observed 67 heads. And maybe if you do it 1,000 times, you have 55% of the time it's heads. And the more and more and more and more you do it, the closer that these will eventually match one another. And that is what the law of large numbers means. Okay, so now we have some practice problems. And what I'm going to do is pause our video so you can fill in any notes you need, and we can jump in with an example